Alright, for this problem we're going to do something a little different because I've already typed up a solution to this and I don't want to have to rewrite all these words, and so I might as well just show you what I have from before. So here's the problem statement. We have this product, and instead of just stopping here, I mean, if you want to take this and read this yourself, you can just stop it, but let's talk through this. Also, I haven't read through this since I typed this up, and that was like a couple months ago, so we'll see how this goes. But anyway, so we're going to let p, lowercase p, be just the normal product because that will help out with differentiating between them. So you got proof associativity, so you take three elements in M, so then we know that the product P is associative, just because it's just the normal product, just because it's a product of a monoid, and so by definition or by assumption it's associative. And so then when you do all the calculation, when you do this PM product where you basically stick little m in the middle of everything, you just do that and see what you get, and then you once you get to this middle step here, then you just switch it around. You use the associativity of little p, and you just use that there, and then you bunch it back up, and it gives you exactly what you want. Now, this does look a little weird because we're doing this in instead of the normal way that you use this C associativity here, we're actually seeing it with we're actually writing out in terms of like PM of, and then writing out the two arguments. So it looks a little weird, but you can just convince yourself that this is just what associativity means. So this thing is associative. So under what conditions does there exist a unit relative to this product? So then we want sufficient and necessary conditions. So let's see here. So we're going to say if you have a product row on M, a row inverse is the inverse. A row inverse for an element little m in big M is an inverse for little m with respect to the product row, and the row unit, blah blah blah. So then that will help us differentiate between a P unit and a PM unit, and a P inverse and a PM inverse, because these are all going to come into play, or at least some of them. So anyways, I claim that M contains a P inverse. That's okay. M contains a P inverse for little m if and only if big M contains a PM unit. So we do one direction, and you suppose that capital M does have a P inverse. So we'll just call this E sub M. And so you just write out what that means by definition. It means that if you multiply M times EM, it's the same thing as EM times E. Wait a minute. M has a P inverse. If this P inverse is EM's, then this should be MEM equals EM equals M. So there we go. So good thing I'm going back to this. So anyways, so let's take some element. So that's what it means. That's what we can conclude from knowing that capital M contains a P inverse. And so now we want to prove that capital M contains a PM unit. So what we want to do is we want to prove that this E sub M is the PM unit. So take an element A in capital M, then A equals, by definition, wait a minute. Right. A equals AE, which equals A MEM. No. I got the this is a P inverse for M. A P inverse for M means that M times EM. This is going to be the identity E here. Okay, so I over corrected myself, which made it wrong, and now I got it right. So this first E should have been an M, but this should still be an E because that's right. Okay, it's yeah, because E sub M is going to be the inverse of M with respect to P, but it's also going to be the unit of P sub M. So anyway, so you let A be in capital M, and then A is equal to AE because E is just the this is P multiplication in P, so E is the P unit, so that's fine. And then because M and EM are inverses, they're P inverses, and so you can replace the A with that. So I guess this wasn't really necessary, but whatever. And so then this just by definition is PM A EM. And so this means that if the product of A with EM is A, and so that's that. And also you do the same thing. You have A equals EA equals EMMA equals PM EMA, and so A equals PM EMA. So that means precisely that EM is a PM unit. Well, is a PM unit. So now that takes care of that direction. And so now we go to necessity. So suppose that capital M does contain a PM unit, and again we're going to denote it by EM. And then you just choose some A and M, and then what happens? Let's see here. So if M contains a PM unit, then you choose some A and big M, and then PM A and EM equals PM EMA equals A. That's just by definition of having a PM unit. And so what does that mean? That means if you expand out what PM AEM means, that's just A M E M, just by definition. And so that implies that MEM equals E. Ooh, why does that follow? Because what we want to do is we want to get... Can we just cancel the A's on the end like that? I've been doing this a lot lately. I tried quitting coffee, and it seems to have had an effect on my cognitive abilities. But for some reason, I'm blanking on this at the moment. My gut's telling me that because we're trying to prove that let's see here, this is a monoid, so we don't have invertibility, so you don't necessarily have cancellation. So how can you go from knowing that A equals AMEM to having that MEM equals E? Well, wait a minute. I guess what you could do is here's how I think this should go. A equals PMA EM equals AM EM, and A equals PM EMA, because we know these two equalities we know. Well, actually, all of these equalities we have already. It's just that cancellation part. But now, as after we do this, we know that AMEM equals A equals EMMA. And so that means precisely that EMM is the identity E. That we do know, because that's what the identity is by definition for a monoid. It is when you have AMEM equals A equals EMMA. And so EMM equals E, and so then you could do the same thing for M and EM flipped. Oh, I see. That's sort of the main issue here, is the flipping the EM and the M. Okay, so hold on a minute. A equals PM AEM. So we know that M contains. Oh, okay, hold on. So wait. EM is a PM unit. Okay, let's review this. EM is a PM unit, meaning that PM AEM equals PM EMA equals A. Expand that. That means that EMMA and AMEM both equal A. So these are not the same thing. Yeah, I'm not convinced that this is working. Here, I'm gonna pause this for a second and then come back to this. I'm probably just not seeing something simple. Alright, I figured it out. Something seemed fishy about this, and I was right. Oh, I was spoiling what I changed there. And that's because something seemed weird. Was where's this A coming from? It's useful for telling us this thing, but then why do I keep using it? Well, it turns out it's not important at all. We want to look is not A, is E, the identity in P. So yeah, because this A was just some random element. We don't care. There's no reason. You shouldn't expect just a arbitrarily chosen element to be able to prove something useful for you. So anyways, so you look at E, and E is PME blah blah blah, and this is E blah blah blah, and that's just equal to meme. And what else do we have? We also have E equals PM EME, which is not Emma but ME, which equals M. And this implies that EMM, this implies that MEM equals EMM equals E. There we go. Okay, so that's how we get there. And this means precisely that EM is a P inverse for M. And so that does it. Hence, capital M contains a P inverse for little m, if and only if capital M contains some PM unit. And we are finally done.